This video is going to discuss limits at infinity. The idea, since we're approaching either minus infinity or positive infinity with a certain type of function, is really what is the end behavior of the function. In the case of a polynomial function, which it can be expressed in this form, so a sub n x to the n plus a sub n minus 1 times x to the minus 1, etc., down to a sub naught, is what is the degree. Okay, so these two represent the degree of the function. So is it an even function, or is the highest power even? Is the highest power odd? And then what is the leading coefficient? So for that term that has the highest appearing exponent, what is the coefficient, if it's positive or negative? And then this notation is arrow notation. What this means is, think of it as an ordered pair telling us, okay, what is the value of the polynomial as x approaches minus infinity? And then the second coordinate, if you will, is telling us what happens to the function as x goes to positive infinity. Okay, so in this first example, limit as x goes to infinity of 2x is 6, etc., we see that the 6 is the highest appearing exponent, so that means n is even. And then the 2 is a sub n, and that's telling us that a sub n is positive. So then I need to find where that is on my table. So a sub n positive and n even, that is right here. Okay, now with that in mind, I need to say, okay, well, as x goes to infinity, which coordinate is that? That's going to be the second coordinate. So if it is pointing up at all, that means it's approaching positive infinity. If it's approaching negative, or if it's going down, if it's pointing down in some fashion, that means that it is approaching negative infinity. Let's do another example. So in this example, p is going to approach negative infinity, and then I have my polynomial function. This function has a degree that is odd, okay, and its leading coefficient is still positive, so I need to find that on my table. So n odd, a sub n positive, that's right here. Okay, so that means that now if I'm approaching minus infinity, that's the first coordinate in these two. So again, this limit would approach minus infinity. Okay, now just a note of clarification, infinity is not a number. Okay, infinity is not a number, it's a concept. So technically what we should be saying is that the limit does not exist. The limit is typically known as a finite value, but just so we get a general idea of what is happening to the function over time, or as the value of the independent variable increases, we can communicate infinity or minus infinity. Another acceptable response might be does not exist, okay, or DNE. Another type of function that we know the end behavior really well of is a rational function. So a rational function, just to remind you, is of the form p of x over q of x for some polynomials p and q. So technically every polynomial function is a rational function where the denominator polynomial is just 1. Okay. But with the rational functions, if we're looking at end behavior, we know that rational functions should have a horizontal asymptote, and there's different ways that we can find that if we recall some of our pre-calc skills. Okay, so if we call the degree of the numerator polynomial, okay, so degree of p, we call that n, and we call the degree of q, the denominator polynomial, m, then leading coefficient, and also we need to know the leading coefficient. So with those degrees, we can say, okay, well, what's the leading coefficient? And the leading coefficient for p we're going to say is a, leading coefficient of q is b, and then with that we can get the horizontal asymptotes in some cases. So if n, so again the degree of the numerator polynomial, is bigger than m, the degree of the denominator polynomial, then there's going to be no horizontal asymptote. Okay, that's just not going to exist. If the numerator degree is less than then the denominator degree, then it's going to be a horizontal asymptote at y equals 0. If they're equal, that's when we need to take the ratio of their leading coefficients, so a to b. And so what this means for us, when we look at the limit of a rational function, we can break it up into 3 cases. Those same cases as before. So if n is bigger than m, so again, numerator degree, denominator degree, if n is less than m, and if n is equal to m. So if it's greater, then we just say, in terms of a limit, there's no horizontal asymptote, so the limit does not exist. If it is less, it's going to approach 0. If it's equal, a over b, for whatever those leading coefficients are. Okay, and note that this does hold whether it approaches positive or negative infinity. Okay, so a quick example here. Limit as x approaches minus infinity. I don't really care about it too much. And I put in, and I can get my, I get my rational function here. So if I look at the degree of the numerator is 5. The degree of the denominator is 4. Okay, so we're actually in this case here where the numerator degree is bigger than the denominator degree. So I'm just going to say the limit does not exist. Okay, and we can also see this in an algebraic way if we use the following theorem. So for n a positive integer, we can say that we actually know that the limit as x goes to positive or negative infinity of 1 over x to any power, any positive power, is 0. Okay, so we get a second method. The second method is we want to divide by the highest pairing power of x in the denominator, because if we divide by the highest pairing power of x, it might actually be in the numerator, and then it would cause us to divide by 0. Okay. And then use the above theorem to make certain terms 0. So if we follow that process through, okay, I can do a little bit of algebra here. So if we're not super confident in the 5th and 4th power, there's a second way here. We can actually write this as limit as x approaches minus infinity. Now, one note that I'll make as far as notation, every time you work with a limit, if you do not evaluate it, you do need to include this notation. It does, the limit is a value. If you just happen to write the function itself, you're comparing two things that are not equal. Okay, so now getting back to the problem at hand, I need to divide by the highest power pairing power of x in the denominator. So I'm going to divide by x to the 4th. Okay, divide each and everything by x to the 4th, or x to the 4th. So first one's going to be over x to, so negative 3x to the 5th over x to the 4th plus 2x squared over x to the 4th minus 1 over x to the 4th all over 4x to the 4th over x to the 4th plus 5x squared over x to the 4th plus x over x to the 4th. Okay, now when we did that, we actually divided by a form of 1, so I did not change the value of the limit. And if I go ahead and simplify this now, just simplifying powers of x, x to minus infinity, minus 3x, and then this is going to be plus 2 over x squared minus 1 over x to the 4th all over 4 plus 5 over x squared plus 1 over x to the 3rd. Okay, and when I do this, I apply the above theorem, and we're going to learn the limit laws, which allow us to do this more formally, but this is going to go to 0 because it contains the power of x in the denominator, and my limit is infinite. a form of infinity. So 0, 0, and 0. Okay, so in value, not as an expression, or not as a function, but in value, this would be equivalent to the limit as x goes to infinity of minus 3x over 4. And I can do this computation and I actually see that, okay, this is minus infinity, but again, we could say that minus infinity technically isn't a value per se, so our answer that we got above of does not exist is appropriate here. Alright, some other notes about the other types of functions we might encounter. Trig functions in general, they're periodic, so if we look at a limit as they go to infinity, they're going to continue to oscillate, so they do not approach a single value, so we would say that the limit does not exist. There's notes about convergence and divergence here. I'll let you read that. Exponential functions and logs, again, so logs have a restricted domain, so they can really only approach positive infinity. Again, if we have a base function, if we have transform functions, that may change. But a log function, as we go to positive infinity, will go to infinity as well, just very, very slowly. Exponential functions, again, if we go to minus infinity, they actually have horizontal asymptote at 0 in that case. If they go to positive infinity, they do not have a horizontal asymptote, so we would say that the limit approaches infinity, but again, as a value, there isn't a limit value, so the limit technically does not exist.